Dear students, let us begin the third part of the lesson, in which you will learn about confidence coefficient and power of the test. The confidence coefficient, also called the confidence level or degree of confidence. It represents the likelihood or probability that a calculated confidence interval contains the true population parameter. It is expressed as a percentage such as 95% or 99% or 90%. A higher confidence level, it implies a wider interval that is more likely to capture the true parameter value. A lower confidence level results in a narrower interval, but with a higher risk of not including the true value. If the CL equal to 90%, then in 90 out of 100 samples, the interval estimate will enclose the true population parameter. Here alpha is the area under the curve distributed equally under both the tails of the curve. Further, this area indicates the levels of statistical significance. Mathematically, alpha plus CL is equal to 1. We can see the pictures of common levels of confidence. If confidence level 1 minus alpha is equal to 0.90, then alpha equal to 0.10. If the confidence level 1 minus alpha is equal to 0.95, then the alpha level alpha is equal to 0.05. If 1 minus alpha equal to 0.99, then the alpha is equal to 0.01. Then we can find the Z value corresponding 1 minus alpha. Then we can see also in this picture, this is for 90% level of significance, this is 95% of the confidence level, and this is a 99% of the confidence level we can see here. From this diagram, this is a non-rejection region, that is acceptance region. These two ends, two tails are rejection region. This is a mu value, central value. Then for example, 80 male students are randomly chosen and yield an average of 6.6 hours of sleep with the standard error of 1.8. 65 females are randomly selected with an average of 6.9 hours of sleep with a standard error of 1.5. Construct a 95% confidence interval for the difference between the two mean sleep hours for males and females. Given information for males, x1 bar is equal to 6.6, s1 is equal to 1.8 and n1 is equal to 83. And also given information for females, x2 bar is equal to 6.9, s2 is equal to 1.5 and n2 is equal to 65. From these informations, we can find degrees of freedom. It is equal to n1 plus n2 minus 2, it is equal to 146. Then we have a 95% of the critical value, that is alpha at the level of alpha is equal to 0.5, it is equal to 1.98 from the table value. Then we can find f equal to s1 square by s2 square, it is equal to larger variance divided by smaller variance, it gives the values 1.44. Since our f value is equal to 1.44 is less than the 1.98, so we can pool our variances. Then we can find SP is equal to this formula, we can use this formula, SP is equal to 1.68. Then we can construct, using this formula, we can construct the 95% of the confidence interval. It is nothing but minus 0.85 and 0.25. Now we can define confidence intervals. For normally distributed data, approximately 95% of the individual measurements lie within the two standard deviations of the mean. Difference between two sample means is approximately normally distributed in large samples, regardless of the distribution of individual measurements. We can use this formula to find out the confidence intervals. y1 bar minus y2 bar, it follows normal distribution with the mean mu1 minus mu2 and variance square root of sigma 1 square by n1 plus sigma 2 square by n2. Thus, we can expect with 95% of the confidence level that our sample mean difference lies within the two standard errors of the two difference. 1 minus alpha 100% confidence interval for the difference between two means mu1 and mu2. Large sample confidence intervals for mu1 minus mu2 is nothing but y1 bar minus y2 bar plus or minus z value at alpha by 2. Standard level of confidence is 95%, that is z at 0.025 is equal to 1.96, it is approximately is equal to 2. 1 minus alpha into 100% confidence interval and two-sided test reach the same conclusions regarding whether the difference of two means is equal to 0. The next we can define power of a test. Power of a test, it is against a specific alternative value, is the probability that the test will reject the null hypothesis when the alternative is true. The power of a statistical test is the probability of correctly detecting a true effect or difference. It is influenced by factors such as sample size, effect size, significance level and data variability. It helps researchers to make informed decisions about study design and interpret the results of hypothesis testing. So, we can see this picture, the power is defined as a 1 minus beta. The power is the probability of avoiding a type 2 error. In this picture, as n increases, alpha stays the same, alpha is nothing but level of significance, beta goes down and power increases. Example, a study to compare the effectiveness of two different teaching methods on student performance. We randomly assign 100 students to two groups. Group A receives method A and group B receives method B. At the end of the study, we measure the average test scores for each group. For this problem, the null hypothesis is there is no significant difference in the average test score between the two teaching methods. The alternative hypothesis HA or H1 states that there is a difference. After the t-test, the value of p is significant, therefore, you reject the null hypothesis and conclude that there is a statistical significant difference in average test scores between the two teaching methods. The power of the test in this scenario would refer to the probability that you correctly rejected the null hypothesis when it was false. In other words, it measures the likelihood that you detected a true difference in a student performance between the two teaching methods. If your study has a high power, it suggests that you have a good chance of finding a significant effect if there was one present. On the other hand, if your study has a low power, it implies that you have a higher risk of failing to detect the difference even if it truly existed. Power is nothing but probability a test rejects H naught, depends on the difference between two means. If H naught is true, the power can be defined as follows. Power is nothing but probability of type 1 error, it is equal to alpha. When H naught is false, the power is defined 1 minus probability of type 2 error, it is equal to 1 minus beta. This is one more example we can see. H naught from mu1 minus mu2 equal to 0. Alternative hypothesis H1 or HA is equal to mu1 minus mu2 either greater than 0 or less than 0 or is not equal to 0. Also given information are sigma 1 square equal to sigma 2 square equal to 25, n1 is equal to n2 is equal to 25. Our decision rule is reject H naught at the level of significance 0.05 if the Z observed values is equal to y1 minus y2 divided by square root of sigma 1 square by n1 plus sigma 2 square by n2. It is also equal to y1 bar minus y2 bar divided by square root of 2. It is greater than or equal to 1.645 and also it is equal to y1 bar minus y2 bar, it is greater than or equal to 2.326. Now, suppose in reality that mu1 minus mu2 is equal to 3.0 when HA is true. Power now refers to the probability we reject the null hypothesis when it is correctly. The sampling distribution of the difference in sample means has to be approximately normal with mean 3.0 and standard deviation, or it is also called standard error, is 1.414. Now, the decision rule. We conclude that subpopulation means differ if the sample mean for group 1 is at least 2.326, higher than the sample mean for group 2. Power for this case can be computed as the probability of y1 bar minus y2 bar should be greater than or equal to 2.326. That is, y1 bar minus y2 bar follows normal distribution with mean 3 and variance 1.414. Also, probability of y1 bar minus y2 bar greater than or equal to 2.326, it is equal to probability of z greater than or equal to 2.326 minus 3 divided by 1.41, it is equal to minus 0.48. If you find this value of z, then it is equal to 0.6844. Also, else being equal to, as a sample size increases, the power increases. As a population variances decreases, also power increases. As the true mean difference increases, power increases. So, we can see the power of a test through this picture. This is nothing but probability of acceptance. Probability of accepting H naught given H naught is equal to 0.95. Probability of rejecting null hypothesis H naught against H1 or HA is true, it is equal to 0.6844. Also, we have another diagram for power of a test. In this diagram, it shows that if the sample size or n1 is equal to n2 is equal to 100, we can have like this, and also n1 is equal to n2 is equal to 25, we can have like this power of a curve. Then power curves for group samples sizes of 25, 50, 75, 100 and varying true values, the difference between two means mu1 and mu2 with sigma 1 is equal to sigma 2 is equal to 5. For given mu1 minus mu2, the power increases with the sample size. For given sample size, the power increases with the mu1 minus mu2. Let us summarize what we have learnt from this lesson. In this lesson, we have gone through the notion of the true positive, false positive, true negative, false negative with examples, and also we have gone through the concepts of types of errors and level of significance. The power of the test and confidence coefficient also discussed in detail in this lesson with certain examples. I hope these concepts will be helpful to you in your research. We have completed our lesson on the errors in hypothesis testing and power of a test. Thank you.